In this video lecture, we will discuss aromaticity in benzoid and non-benzoid compounds, Huckel's rule, and what is anti-aromaticity. So, to begin with, let us see what are aromatic compounds and how they are defined. So, aromatic compounds can be defined as compounds that benzene resembles with benzene in their physical and chemical properties. So they resembles with benzene in their physical and chemical properties. For example, these compounds they possesses very high unusual stability as compared to aliphatic conjugated system. They are more stable as compared to aliphatic conjugated system. At the same time, these compounds, even though they have very high unsaturation, that means number of double bonds are present in these aromatic compounds, but they do not undergo addition reactions. They resist addition reactions even in presence of very high unsaturation. But rather than undergoing addition reactions, they undergo electrophilic substitution reactions. Okay. So the stability of these aromatic compounds is given in terms of resonance energy. And this resonance energy, it can be defined as the energy difference between actual calculated energy of that particular molecule and energy of most stable resonance hybrid. For example, benzene, as we have discussed, it's a very first aromatic compound. So if you draw the structure of benzene, so this is benzene and it's a most stable aromatic compound. Okay. So the any compound that resembles with this benzene in their properties, physical and chemical, will be called aromatic compound. Now the resonance energy can be calculated from the heat of hydrogenation. Now heat of hydrogenation means amount of energy which is released when one molecule of hydrogen or one mole of hydrogen is added to the double bond. So let us take the example and calculate this resonance energy of this benzene molecule. Let's see the resonance energy of this benzene molecule, which is a stable molecule as compared to conjugated system. Now suppose you have cyclohexene. Now in a cyclohexene, you have a single double bond. And if you do hydrogenation of this cyclohexene, that means if you add hydrogen to this double bond, it will become cyclohexane, and energy is released which is called heat of hydrogenation around minus 28.6 kilocalories per mole. Okay, this much of energy is released. So now if you take two double bonds inside the ring, so for one double bond this much of energy is released. So if you take two double bond inside the ring, and if you do their hydrogenation, that means you have to add two molecules of these hydrogen. So again you are going to get cyclohexane, and here the expected value of energy, since for the one double bond this much of energy is released, so for two double bonds we have to multiply this energy by 2. So it will be 2, it will be around, yes, 57.2 kilocalories per mole. So this much of energy is expected to released. And similarly, if you consider so this is cyclohexadiene, this much of energy is expected to released. Now suppose you have a hypothetical molecule in which three double bonds are present inside the ring. And suppose this is cyclohexadiene. So I am not talking about this benzene. Now this benzene is stabilized by resonance. Okay, it is stabilized by resonance, and its actual form is a resonance hybrid. We write the structure of benzene like this, in which all of these double bonds they are completely delocalized. So this is actual structure of benzene. So this is actual structure, and these two are hypothetical structures in which three double bonds are there inside the cyclohexane ring. This is the actual structure. That's why we write benzene ring like this. Okay, with complete delocalization of electrons. So if you consider this cyclohexatriene in which three double bonds are present inside the benzene ring, that is these resonance structures, kind of resonance structures, these two, and if you do its hydrogenation, so the expected value, since there are three double bonds, so the expected value will be, you have to multiply this minus 28.6 with 3. Okay, so you have to multiply it by 3. Okay. So this will give the corresponding value. This will give the corresponding value of minus 85.8 kilocalories per mole. So this is for the cyclohexatriene, this hypothetical molecule, for this hypothetical molecule. Okay, but when you take an actual benzene molecule, so when you take actual benzene, so actual benzene is this one, even though it also has a three double bond. So when you take actual benzene and if you carry out its hydrogenation and to get the cyclohexane, in that case the amount of energy released, the actual amount of energy released is 49.5 49.3 kilocalories per mole. So this is actual amount of energy which is released, and this was the hypothetically expected. So this is actual amount of energy is released. That means in benzene these double bonds, they have a lesser energy or they have a more stability. So your resonance energy can be written as energy of the actual molecule. So this is energy released in actual molecule. Okay, so it will be minus 49.3, and the energy of the most stable resonance structure. So this is a hypothetical resonance structure of this benzene, and this is its expected energy. So it will be minus 85.8. So that comes to be 36.5 kilocalories per mole, or approximately 36 kilocalories per mole. So this energy is a resonance energy of benzene. That means this benzene, it is stable by 36 kilocalorie per mole as compared to this hypothetical cyclohexatriene molecule. So more resonance energy, more is stability of a particular aromatic compound or a particular compound. Okay. So now let's look at the how we define any compound as the aromatic or a non-aromatic or anti-aromatic compound. Now we can define any compound as the aromatic or anti-aromatic or a non-aromatic compound depending upon the set of rules which are given by the Huckel. That is called Huckel's rule of aromaticity. So this is very important. Huckel's rule of aromaticity. So what Huckel's rule says, it gives a few conditions. On the basis of that, we can define whether molecule is aromatic, non-aromatic, or anti-aromatic. And what are those conditions? And the very first condition is molecule must have cyclic planar structure. That means structure of the molecule must be cyclic and it must be planar. Therefore, to acquire planar structure, so each atom, it must have sp2 hybridization with unhybridized p atomic orbital, with one unhybridized p atomic orbital. Okay. The second condition is these unhybridized p atomic orbitals, they must overlap with each other to give uninterrupted cloud of pi electrons. So first condition is molecule must have cyclic planar structure, and planar structure is possible only when they have sp2 hybridization. So when there is sp2 hybridization, so there must be at least one unhybridized p atomic orbitals, and these p atomic orbital, since they are parallel to each other, so they must overlap to give uninterrupted cloud of pi electrons. And if this uninterrupted cloud of pi electrons consists of 4n plus 2 pi electrons, now where n may be 0, 1, 2, 3 and so on, in that case compound will be called aromatic. So in that case compound is aromatic. On the other hand, if this uninterrupted cloud of pi electrons completely delocalized pi electrons, they have 4n pi electrons, in that case it will be anti-aromatic. On the other hand, if compound does not satisfy any of these conditions, that means compound is either not cyclic nor planar, in that case it will be called non-aromatic compound. Okay, so depending upon number of pi delocalized pi electrons, it will be aromatic, anti-aromatic and non-aromatic. In aromatic compounds it must have 4n plus 2 pi electrons. In anti-aromatic they must have 4n pi electron, while if it does not cyclic or a planar, it will be called non-aromatic compound. Now if you look over the stability, order of stability of these compounds, in that case aromatic compounds, they have maximum stability due to delocalization of pi electrons. Then you have non-aromatic compounds, and these anti-aromatic compounds, they have least stability. Okay, anti-aromatic compounds, when there are 4n pi electrons, where n may be 0, 1, 2, 3 and so on, they have least stability. Okay, so this is a very important Huckel's rule of aromaticity. So let us see the type of different aromatic compounds. Now the aromatic compounds, on the basis of their structure, they can be classified into two categories. One are benzoid aromatic compounds and another are non-benzoid aromatic compound. So as name suggests, benzoid aromatic compound means they consist of benzene ring, at least one benzene ring in their structure. While non-benzoid aromatic compounds, they do not have, they are aromatic compounds, but they do not have benzene ring in their structure. Okay, so they can be defined as benzoid or non-benzoid aromatic compound. Benzoid aromatic compounds means these are aromatic compounds which consist of at least one benzene ring in their structure, while non-benzoid aromatic compounds means they do not have any benzene ring in their structure. Okay, so that are called non-benzoid aromatic compounds. So let us see the examples of these benzoid and non-benzoid aromatic compounds. Okay, so the very first example is a naphthalene. Benzene we have already discussed, so benzene is also a benzoid aromatic compound, of course. The very first example we will take of naphthalene. Okay, so naphthalene is an example of benzoid aromatic compound. So the structure of naphthalene is this one. So this is your naphthalene. Okay, and so you can see in naphthalene each carbon atom is sp2 hybridized. So there's a one unhybridized p orbital containing one electron each, and they overlap to form a complete delocalized pi electrons. Now you can see the number of pi electrons are 2, 4, 6, 8 and 10. So this is system of 10 pi electrons. So total number of 10 pi electrons are there, 10 pi electrons. So it satisfies 4n plus 2 pi electron rule for n is equals to 2. For n is equals to 1, it is benzene ring. So it satisfies Huckel's rule. How it satisfies Huckel's rule? First of all, it has a cyclic structure. It has a planar structure. It has a cyclic planar structure with complete delocalization of pi electrons through unhybridized p atomic orbitals with total 10 pi electrons, which satisfy 4n plus 2 pi electron rule. Therefore, this naphthalene molecule is a aromatic molecule. This naphthalene molecule is a aromatic molecule. Now, if you draw its resonance structure, so let's draw the resonance structures for naphthalene. So, okay, let us draw the resonance structures of naphthalene. Suppose this is your carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Now, in polycyclic systems that consist of more than one benzene ring, you can see this ring, it can be considered as a benzene ring as 3 double bonds are inside this cyclic ring. So this is considered as a benzene ring, while this another ring, it has a 2 double bonds in conjugation. So this can be considered as just butadiene portion. So you can see this butadiene portion is attached with this benzene ring. Now let us see how to write resonance structures in these cases. In case of polycyclic system, I will give 2 or 3 examples, remaining you can do it by yourself. So while writing resonance structures, the very first thing is we rotate double bonds which are present inside the benzene rings. Okay, we rotate double bonds present inside the benzene rings one by one sequentially until all double bonds they goes at the outer portion of ring. Now if you consider this small molecule as the ring, you can see this in this first benzene ring, this is a benzene ring, this double bond is present inside the benzene ring. So we will rotate these double bonds in such a way that this double bond goes at the outer portion of this ring. So we will rotate it. So we can rotate it like this. You have to rotate it only one way. Okay. So you will get this structure. So this double bond will shift over here. Okay. This double bond shifted over here. This shifted over here. This shifted over here, this shifted over here. Now you can see in this structure, in this resonance structure, all double bonds they are present at the outer portion of the ring. They are present at the outer portion. Then in next step, when that happens, in next step, we rotate all these double bonds in one step at the outer portion, at the outer region. We should not move this double bond inside, but we should move these double bonds on this outer portion of ring. So let's do that. So I will rotate these double bonds like this. So this will goes over here. This will go over here. This will go over here. And this double bond will move over here. Okay, we should not move inside. We have to move then on the outer portion of this ring. So this gives you a double bond over here. Okay, and this double bond is shift over here. This shift over here. This shift over here, and then the shift over here. Okay. Then in next step, you again rotate double bonds inside the any new benzene ring which is formed. So you can see this is new benzene ring over here which is formed sequentially until you get this first arrangement back. So we will move this, rotate the double bond of this new benzene ring. So I can move like this. Okay. So when I move like this double bond shift over here. Okay, you can write in this side or this side, that means same thing, this one and this one. So now you can see reductancy has happened, and this structure and this structure, they have a same arrangement. So this structure, so suppose this is 1, 2, 3 and 4. So this structure number 4 and structure number 1, they have a same rearrangement of these double bonds. So we neglect this structure. So these three are the resonance structures of naphthalene molecule. So we can write resonance structures of any molecule by using this technique. Okay. Now the another point over here, you can see in these three resonance structures, if you look over the bond at C1 and C2 position, if you look C1 and C2 and C2 and C3. So you can see at C1 and C2 there are two resonance structures that have a double bond at position C1 and C2. But for C2 and C3, there's only one structure which has double bond, that is this structure, while in remaining two structures it has a single bond. So that means C1 at C2 it has a more double bond character. It has a more double bond character as compared to C2 and C3, which has a more single bond character. Okay, so this is also evident from their bond length. Now, if you look over the bond length, you can see C1 of C2, it has bond length of 1.36 angstrom, while C2 and C3, it has a bond length of 1.415 angstrom. That means this C1 and C2, it has a more double bond character. And this is also called partial bond fixation. This property is also called partial bond fixation. And since this C1 and C2, it has a more double bond character, so this C1 and C2 position is more reactive. This position is more reactive, and addition reaction will take place over the C1 and C2 position more rapidly as compared to C2 and C3, which has a less double bond character. Now, further, as I told you, this naphthalene molecule, you can consider this as a 6 pi electron system. That's your benzene system. And this is your butadiene system, which is a 4 pi electron system. And due to this region, this naphthalene molecule, it's more reactive than aromatic benzene molecule. Moreover, the resonance energy for this naphthalene is 61 kilocalorie per mole. Resonance energy is 61 kilocalories per mole. Now let's take the second example, and the second example of this benzoid aromatic compound is anthracene. Now in anthracene, three ring molecules, three benzene rings, they are joined together. So this is your anthracene. So three rings are joined together. Okay. So this is your anthracene molecule. And if you want to number these anthracene molecule, we can number it as, say this is 1, 2, 3, 4, then 5, 6, 7, 8, 9, and 10. So this is 11, 12, 13, and 14. Okay. Now, again, this anthracene molecule, it has a cyclic planar structure. It molecule has a cyclic planar structure. Okay, and since each carbon has a sp2 hybridization, so it is cyclic planar structure with 2, 4, 6, 8, 10, 12, and 14 with 14 pi electrons. So it satisfies Huckel's 4n plus 2 pi electron rule for n is equals to 3. It satisfies Huckel's rule for n is equals to 3, and it's a aromatic compound. Okay. Now here also there is a partial bond fixation, and at position number 9 and 10. So it's partial bond fixation at position number 9 and 10, which has more double bond character. At position 9 and 10, it has more double bond character, and that can be explained by using resonance structures where double bond occurs in more resonance structures at position number 9 and 10. So let us draw the resonance structures of this anthracene molecule. Resonance structures of anthracene molecule. So as we have discussed previously how to write resonance structure, First of all, we have to rotate double bonds present in benzene ring one sequentially, so that all double bonds they goes at the outer portion of ring. So this is first benzene ring over here. You can see only this double bond is inside the ring. Here they are both are outside. Here both are outside, even though they are not benzene rings. So we have to rotate these pi bonds so that they moves outer ring. So I can rotate them. Okay, so I can rotate them like this, so that it moves over here, it moves over here, it moves over here. Okay, so you get double bond over here, you get double bond over here, you get double bond over here, then double bond like this. So now you can see all double bonds there goes to the outer ring, outer portion of this ring. Then in next step what we do is we rotate this double bonds on the outer side over this whole molecule. Over this whole molecule, we rotate them on the outer side. So I can rotate. So this goes over here, this moves over here, this moves over here, this goes over here, 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 and here. This one. So this double bond comes over here, this one over this position, this comes over this position, it goes over here, this position, and double bond over here, double bond over here. Okay, so what was the next step? The next step was we have to rotate the double bonds inside the any new benzene ring which is formed until we get first arrangement back. Okay, so this is your new benzene ring, so we rotate double bonds inside this benzene ring. Benzene ring means when you have three double bonds inside the cyclic ring, so that ring we will call it benzene ring. So it remains here, so we have to rotate these double bonds, this. Okay, and now you get this middle ring as the new benzene ring, because you have double bond here, double bond here, and double bond here. So we rotate it again until we get this first arrangement back. Okay, until we get first arrangement back. So double bond over here, double bond over here. So we rotate inside this middle ring. So you get double bond over here, double bond over here, here and here. Now you can see this is same as that of first structure. This is same as the first structure, because here also you have a benzene ring on the first ring. So here you have a benzene ring, then two double bonds over this position, two double bond over this position, and two over this position. So we neglect this structure. So these are four resonance structures of anthracene molecule. These four are the resonance structures of anthracene molecule. Now you can see in all these resonance structures, there is a double bond character at position number 9 and position number 10. So this position number 9 and position number 10, it has more double bond characters, because in each structure there is a double bond present over these two positions. So that is why it has a more double bond character, and this position number 9 and this position number 10 is more reactive. Okay, and addition reaction or normal reaction take place over position number 9 and position number 10. For example, if you carry out the addition reaction, it will take over position number 9 and position number 10 in case of anthracene. Okay, and the resonance energy for this molecule is 84 kilocalories per mole. The resonance energy is 84 kilocalories per mole. Okay. The third one, the next aromatic benzoid aromatic compound is phenothrene. The next aromatic compound is phenothrene. Now phenothrene is a isomeric form of anthracene. So it also have a 3 aromatic rings. Okay, but it has isomeric structure. Suppose I put double bond over here, then here, and then here. So it's a again aromatic compound, and if you want to number them, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now here this position number 9 and 10, it has more double bond character due to the partial bond fixation. Okay, again this compound is aromatic as it has a cyclic planar structure with complete delocalization of these pi electrons with again uh, 6, 10 and 14 with again 14 pi electrons. So it satisfies Huckel's rule. Okay. Now resonance structures, you have to write them by yourself as we have discussed method above. So you can write these resonance structures by yourself. Okay. And again, as I told you at position number 9 and 10, in more resonance structures, the double bond is over position number 9 and 10. So it has a more aromatic, more double bond character at position number 9 and 10. Suppose if you carry out any addition reaction, say bromination, this bromine will get added over position number 9 and position number 10. The resonance structures you have to write down by yourself. So it will added over here. As this position it has more double bond character. Now again the resonance energy for this phenanthrene is 92 kilocalories per mole, which is higher than anthracene. So phenanthrene is more stable. Anthracene is 84 kilocalories per mole. So phenanthrene is more stable than anthracene. Phenanthrene is more stable than anthracene. Okay. And the another molecule, which is again isomeric structure of these anthracene and phenanthrene is phenylene. And phenylene is this one. So in exam, normally question comes given examples of benzoid or non-benzoid aromatic compounds. So you have to discuss these examples. There are at least 2 examples. This one. Okay. And here you have a hydrogens. So as such, this is a non-aromatic compound. Why it is all non-aromatic compounds? Because even though it has a cyclic structure, but this carbon, it is a sp3 hybridized. So since this is sp3 hybridized, there is no complete delocalization of electrons. The electrons are not completely delocalized. This carbon is a sp3 hybridized. So delocalization of electrons is blocked over here. So this is a cyclic structure, but electrons are not delocalized. And this delocalization of electrons is interrupted over here. So this is a non-aromatic compound. There is no complete delocalization. Therefore, these hydrogens, however, these are highly acidic and they can easily lose as H plus ions, giving back anion. So it loses H plus ion in presence of base to give rise to an anion. So if I write the structure of anion, to give rise to a anion with this anion. Now here in this anion, this carbon, it has sp2 hybridization. So now it have a cyclic planar structure with a complete delocalization of electrons. These electrons, they can delocalize. At the same time, it has 2, 4, 6, 8, 10, 12 and 2 electrons from this single negative charge. So it has a 14 pi electrons. Okay, so now it satisfies for n plus 2 pi electron rule for n is equals to 3, and therefore it is a aromatic compound. So phenylene is a aromatic compound. Phenylene anion is a aromatic compound. As such, it's a non-aromatic because there's no complete delocalization of electrons, as here this carbon is sp3 hybridized. So the resonance structures you have to write down by yourself. So these were the benzoid aromatic compounds. Now let's look at the non-benzoid aromatic compounds. Now, non-benzoid aromatic compounds means they satisfy Huckel's rule. They satisfy Huckel's rule, but they do not have benzene ring in their structure. Okay, so there will be non-benzoid aromatic compounds. And let's see the example. The very first are heterocyclic non-benzoid aromatic compounds. Now, heterocyclic means they consist of some heteroatom inside their structure. The very first example of these heterocyclic non-benzoid aromatic compounds are pyridine. It's a six-membered non-benzoid aromatic compound. You have a nitrogen over here. Okay. So this pyridine, it's a non-benzoid aromatic compound. So here also each carbon is sp2 hybridized. Each carbon, so you have 5 carbon, and this nitrogen is also sp2 hybridized. So and it has a 6 pi electrons with a cyclic and planar structure and with complete delocalization of electrons. So pyridine is a aromatic compound. And remember, in pyridine, this pair of electron over nitrogen, it is present in a sp2 hybrid orbital. It's not present in unhybridized orbital. It is present in sp2 hybrid orbital, and therefore it doesn't participate inside the aromatic ring. It is present outside. If you look over the aromatic character of this pyridine, it is less aromatic as compared to benzene. Why it is less aromatic as compared to benzene? Because in case of benzene ring, there are only carbon atoms, but here you have one nitrogen. And since here's 6 pi electrons, they are delocalized over 5 carbons and 1 nitrogen, while here these 6 pi electrons, they are delocalized over all 6 carbon atoms. Now, since nitrogen is more electronegative as compared to carbon, so it held these pi electrons more strongly. Therefore, these pi electrons are not free to delocalized as in case of benzene, where only a carbon are present. So due to the electronegativity of this nitrogen, this pyridine, it is less aromatic as compared to benzene. Okay. And the other example of these heterocyclic aromatic compounds, many examples are there. So if you take 5-membered heterocyclic aromatic compounds such as pyrrole, furon, or thiophene, they are also aromatic compounds. For example, pyrrole, furon, and thiophene. Okay. They are all aromatic compounds which consist of 6 pi electrons. How 6 pi electrons here? This nitrogen is also sp2 hybridized, oxygen sp2, and this sulfur is sp2 hybridized. In each case, this pair of electron present over heteroatom is present in unhybridized p atomic orbital, and it participates in delocalization of these electrons. Okay, so 2 electrons come from this heteroatom, and one from this electron carbon, one from this carbon, one from this, and one from this. So it has a total 6 pi electrons. And if we look over the aromaticity of these pyrrole, furon, and thiophene, the resonance energy for pyrrole is 21 kilocalories per mole. For furon, it is 16 kilocalories per mole. and for thiophene it is 29 kilocalories per mole. That means thiophene, it has more aromatic character as compared to furon and pyrrole. This is due to the low electronegativity of sulfur atom. The order of electronegativity is oxygen is more electronegative than nitrogen and then sulfur. Since sulfur it has least electronegativity, so it can easily give this pair of electrons towards the ring for delocalization of electrons. So that is why it is more aromatic. Similarly, you can also write the resonance structures of these pyrrole, furon, and thiophene. Okay, so they're very easy to write. You can write. You have studied them in BSc also. So by moving this negative charge, you can write the resonance structures. So since this pair of electrons is involved in resonance, so you will get positive charge over here, negative charge will shift over this position, okay, here, and you get double bond here. Then you have to move this negative charge, so it will move over here. This negative pi electrons will move over here. Then this will move over here, and these pi electrons, they will there. And then again over here, so here, so double bond, positive charge will be here, here, and finally be here to give rise to a back fast structure. So these are the resonance structures of pyrrole molecule. So these are the heterocyclic non-benzoid aromatic compounds. Now next is aromatic ions, non-benzoid aromatic ions. Okay, so these are also non-benzoid aromatic compounds, but they are in form of ions. That means they are charged species. So the very first example of aromatic ions is for, let us take for n is equals to 0. That means we have to take 2 pi electron system where n is 0. The very first example is cyclopropenyl cation. Cyclopropenyl cation. Now suppose you have a cyclopropene. So this is cyclopropene. Okay. Now in cyclopropene, this is just one pi bond. So there are 2 pi electrons, and these 2 pi electrons, they are not delocalized. Even though it has a cyclic structure, cyclic planar structure, but there is no complete delocalization of electron, as this carbon, it has sp3 hybridization. So delocalization is not over the whole ring. So what we can do is, if we remove this hydrogen as a H negative ion, so if you remove it as a H negative ion, it will become cation. So like this. And now since this is a cation, so this is carbon is sp2 hybridized, and this vacant vacant unhybridized p atomic orbital is there. So now complete delocalization of these pi electrons, it can take place. So we can delocalize these pi electrons, so it can shift over here. So we can write its resonance structures. So double bond can have positive charge over here, or it can go over here. So positive charge can shift over here. So we can write its resonance structure. So there is a complete delocalization of these 2 pi electrons over this whole ring like this. Okay. Now, due to this complete delocalization of pi electrons, so it satisfies Huckel's rule. There are two pi electrons are there, so 4n plus 2 rule is satisfied for n is 0, and it's a cyclic planar structure. Therefore, this cyclopropenyl cation is a aromatic cation. Okay, it is an aromatic cation. But what about its anion? Suppose we remove this hydrogen as H plus ion. So in that case, it will become cyclopropenyl anion. Now in this case also, there is a complete delocalization of these electrons, as this is also sp2 hybridized. Okay, and they are in conjugation, so there's a complete delocalization of electron. It has cyclic planar structure. However, in this case, it has 4 pi electrons. So 4 pi electrons means it satisfies 4n pi electron rule for n is equals to 1. So in that case, according to definition of Huckel's rule, as we have discussed, this anion is a anti-aromatic. Okay, so this cyclopropenyl cation is a aromatic, and its anion is a anti-aromatic. So this has a least stability. So if you write order of stability, this cation, it has maximum stability, then simple cyclopropene, okay, which is a non-aromatic compound. So this is a non-aromatic cyclopropene, and least one is its anionic, which is an anti-aromatic compound. So that is the order of stability. For example, if you have a chlorocyclopropene, suppose you have this one. So suppose we have chlorocyclopropene, and if you treat it with a silver nitrate, what will happen? This silver nitrate or silver, it will quickly take this chloride as a Cl negative ion to form cation, which is a aromatic. So this will get precipitated and the result get a aromatic cation. So it undergoes a SN1 substitution reaction. Here it can undergo a reaction with nucleophile. So this can undergo a SN1 substitution reaction, and chlorine can be replaced by the another nucleophile, as it can be easily lost as a negative ion. Similarly, more examples are also there. Okay, you can see. Let's take another example for n is equals to 1. That means when n is equals to 1, this means you have a 6 pi electron system. So let's look at the aromatic ion with n is equals to 1 in Huckel's rule with 6 pi electron system. And example is cyclopenta dienyl anion. So it's an example of anion. Suppose you have a cyclopenta diene. Now this is cyclopenta diene. So here you have a hydrogen. So as you see, it's a 4 pi electron system. It's a cyclic, but there's no complete delocalization of electrons, as here this carbon is a sp3 hybridized. For delocalization, it must be sp2. Only it will have a planar structure, and delocalization of electrons will take place through one remaining unhybridized p atomic orbital. So what you will do over here is, suppose you replace this hydrogen as a H plus ion. This hydrogen is highly acidic. In cyclopentadiene, these hydrogens, they are highly acidic and they can be easily lost as a H plus ion in presence. So base, suppose you add ethoxide as a base, it will take this hydrogen as a H plus ion. That results in a formation of cyclopentadienyl anion. Okay, so in anion, you can see this carbon is now sp2 hybridized, so it has a cyclic planar structure. So here it was non-aromatic, but now it has a cyclic planar structure with total 6 pi electrons, 2, 4 and this negative charge. So it has a 6 pi electrons. So now it satisfies Huckel's rule. And therefore this anion is a aromatic compound. Okay, this anion is a aromatic. You can write its resonance structures by moving this negative charge. So you can easily write this resonance structures by moving this negative charge like this. So you can write its resonance structures. And you can also write its resonance hybrid form. So negative charge will be here, and then you again move to this negative charge and so on. So you can write down its resonance hybrid structures, and their corresponding resonance hybrid. So in resonance hybrid, this negative charge will be delocalized over all these 5 carbons. So it's aromatic in nature. Now, what about its cation? Suppose we remove this hydrogen as H negative ion. So in that case, you will get cyclopentadienyl cation. So in that case, situation will be like this. You will have a positive charge over here. So now this cation, again it has a cyclic structure. This carbon is again now sp2 hybridized. So it has a planar structure where delocalization of electrons can take place. But here you have 4 pi electron system, and 4 pi electron system means it satisfies 4 n pi electron rule for n is equals to 1. Therefore, this cation now is a anti-aromatic, which is least stable. So out of these systems, this cyclopentadienyl, since it is aromatic, it has maximum stability. Then this cyclopentadiene, which is non-aromatic, and least stable is cation. And therefore, the cyclopentadiene, it doesn't undergo SN1 reactions. For example, if you have this one, now it doesn't lose Cl negative ion, because if it loses Cl negative ion to form a cation, that will become anti-aromatic and it will be highly unstable. So it does not lose Cl negative ion. So it does not undergo SN1 reaction, as in case of cyclopropenyl anion. Now let's take the other example of aromatic cation. So this was the aromatic anion with 6 pi electrons. So let us take the example of aromatic cation with n is equals to 1, that means with 6 pi electron system. So in exam they may ask you, give an example of aromatic cation, aromatic anion and neutral compound with 6 pi electrons. So neutral is benzene, okay, and cation is we are going to discuss, and anion was cyclopentadienyl anion. So here example is cyclohepta trienyl anion. Sorry, cyclohepta trienyl cation. So we will take an example of cyclohepta trienyl cation. Now cyclohepta means there are 7 carbon with 3 triple bond. Okay, so that is this one. So there are total 7 carbons with 3 double bonds. Now this cycloheptatriene as such is a non-aromatic compound. Why it's a non-aromatic? Because even though it is cyclic, but it is not planar and there is no delocalization of electrons, as this carbon is a sp3 hybridized. So what we can do is, with their total 6 pi electrons, so if you remove this hydrogen as a H plus ion, okay, so sorry, if you remove this hydrogen as a H negative ion, as a hydride ion, so that this bond pair of electron, it is taken by this hydrogen, so that will result in a formation of corresponding cation. So you get a positive charge over here, double bond and double bond. So now this carbon is again sp2 hybridized. All other carbons, they are sp2 hybridized. So there's a complete delocalization of these electrons. Okay, we can also write the resonance structures. You can write by yourself. All other resonance structures, I will write only one. So double bond will shift over here. You will get positive charge over here, here, and so on. So now you can see there are total 6 pi electrons. Okay, and so it satisfies 4n plus 2 pi electron rule for n is equals to 1. At the same time, it has a cyclic and planar structure. So it is a aromatic compound. And this cation of cycloheptatriene is also called tropalium cation. So this is also called tropalium cation. So it's very important. Sometimes they ask you in a question what's tropalium cation. So this cation cycloheptatrienyl cation is a tropalium cation, and the remaining structures you can write by yourself. So the resultant resonance hybrid structure can also be written as, so there will be complete delocalization of electrons, so you can write like this. So this is a aromatic cation. But what if we remove this hydrogen as a H plus ion? So if you remove it as H plus ion, this remaining bond pair of electron will remain on this carbon. So in that case, we are going to get anion like this. Now in this anion, has a cyclic planar structure. Okay, this carbon is again sp2 hybridized, but there are total 8 pi electrons. Okay, you can see there are 8 pi electrons, 2, 4, 6 and 8. So it satisfies 4 n pi electron rule, okay, with n is equals to 2. So this is a anti-aromatic compound. So it's an example of anti-aromatic compound. So we can see this tropalium cation, it has maximum stability than cycloheptatriene, and this cycloheptatrienyl anion, it has least stability. Okay, so this is an example of system of aromatic cation with 6 pi electrons. Okay, so let's take the other example. Let's take the other examples of these aromatic cations. Now let's take the another example with n is equals to 2. N is equal to means aromatic ion with 10 pi electron system. So let's take an example of 10 pi electron system. And the example of 10 pi electron system is cycloocta tetraenide anion. Okay, so it has a 10 pi electron system. Now it's an anion of cyclooctatetraene. Now cyclooctatetraene, that means there are 8 carbon. Now cyclooctatetraene, there, so that means there are 8 carbons are there and 4 double bonds are there. Now since there are 8 carbons are there, so there is a very large angle strain is there. So it has a tub-shaped structure. Cyclooctatetraene as such is a tub-shaped structure molecule due to the strain present in molecule. So it has a structure like this. Double bond is here, double bond is here, here. So it is a not a planar molecule. It's not a planar molecule due to this one. Okay, due to there is a lot of angle strain in this molecule. And due to this angle strain, it's not a planar, but rather it has a tub-shaped structure. And even though it has 8 pi electrons, but even then it's a non-aromatic compound. Why it is non-aromatic, not anti-aromatic? Because it is not a planar, so it is a non-aromatic compound. But when we treat this molecule with any single electron donor such as lithium or potassium, it results in a formation of its dianion, and that's dianion, it has a planar structure. Dianion has a planar structure, so it forms a dianion, double bond, charge here and negative charge here. So this dianion, so this is an only example of dianion with 10 pi electron, that's aromatic. So this dianion, it has 2, 4, 6, 8 and 10. So it has a 10 pi electrons, and therefore it satisfies Huckel's rule for n is 2. And now this molecule is a aromatic. And why it acquires cyclic structure, why it acquires when in dianion form, it acquires planar structure because here it has aromatic character, and the stability arises due to this aromatic character is much more. To acquire this aromaticity is much more as compared to angle strain which is present over there. So it acquires planar structure and it is a aromatic. So now let's take the other example, and the other examples are of anolines. The other example are of anolines. Now, what are anolines? Now, the aniline is a general name for fully conjugated. Anolines is a general name for the fully conjugated monocyclic systems. That means they consist of only one cyclic ring and they are fully conjugated. So these kind of compounds, they are called aniline. The simplest example of aniline is a benzene. So in benzene you can see it consists of only one cyclic ring which is fully conjugated, or cyclobutadiene. So it's a fully conjugated monocyclic system. So that are called anolines. And in anolines, the number of carbon atoms which are present in monocyclic systems, they are written inside the brackets. For example, here 6 carbons are there, so it is a 6 aniline, while here it has 4 carbons, so it is a 4 aniline. In anolines, they have a general formula of CH2M. They have a general formula CH2M. Like this, where M may be any number. So they always consist of even number of carbons as system is fully conjugated. So each double bond, it must have a 2 carbons. So they always have even number of carbons in their structure. So M may be any number, but it always results in an even number of carbons in their structure. Moreover, if this M is odd, for example 1, 3, 5 and so on, in that case this cyclic ring, it will have 4n plus 2 pi electrons. On the other hand, if M is even, that is 2, 4 and 6 so on, in that case it will have 4 and pi electrons. So these compounds, these anilines, they may be aromatic, they may be anti-aromatic depending upon their overall structure. For example, since they are always cyclic, but they are not necessary to be planar. Sometimes they are not planar. But if they are planar and M is odd, they consist of 4n plus 2 pi electrons. In that case, they will be aromatic. On the other hand, if they consist of 4 n pi electrons, that means M is even. In that case, they will be anti-aromatic. For example, 2 aniline, 4 aniline, 6 aniline, they are anti-aromatic. But they will be aromatic only if they have planar structure. Sometimes they do not have planar structure. In that case, even odd anilines, they are not planar. So let's take the examples. So let's take the example. So very first example is of 10 aniline. So 10 aniline means there are 10 carbon atoms inside the ring. So 10 aniline can be drawn as like this. So it's a fully conjugated system. So double bond here, double bond over here, here and here. So it has cyclic structure, and since you can see it has 10 carbons are there, so it's a 10 aniline. So according to its general formula CH2M, M is 5, that means M is odd, that means it has 4n plus 2 pi electrons. So that's true, it has 2, 4, 6, 8 and 10. So it has a 10 pi electrons, that is for n is equals to 2, it satisfies this rule. However, it is not aromatic. Why it is not aromatic? Because it does not have planar structure. Why it doesn't have planar structure? Because these two hydrogens which are present inside the ring, they are very close to each other. So these two hydrogens, they have steric strain and they try to repel each other. So as they repel each other, due to the presence of these hydrogens, they have a non-planar structure. Because of the presence of these two hydrogens inside the ring, they try to repel each other. They produce angle strain in their they produce a steric strain in this their structure, and due to which they do not have planar structure. Similarly, let's take the other example of some bigger aniline. For example, if you have a 14 aniline. Now 14 aniline means you have 14 carbon atoms there. It's a monocyclic ring system with 14 carbons. So here again M will be 7. If you take its general formula, M is 7, so it is odd. So it will have 4n plus 2 pi electron system. Okay. So if I draw its structure, since it is slightly bigger molecule, so this one. So you have double bond over here, here, then at conjugate position, here, this one, here, this left, here, and here. So you can see it has 2, 4, 6, 8, 10, 12, and 14. So it is a 14 pi electron system. So it satisfies Heckel's rule for n is equals to 3. But here also there is a strain between these hydrogens which are present inside the ring. But it is has a planar structure, even though in the presence of this hydrogens due to strain, even though it has a planar structure. So it is a cyclic planar structure with complete delocalization of these pi electrons, and 4n plus 2 pi electrons are there. So this 14 aniline is a aromatic, but it is highly unstable. Why it is unstable? Again, because of the strain produced by these hydrogens. But other bigger anilines, odd anilines, for example, if you take 18 aniline, so 18 aniline that consists of 18 carbons in their structure, it's a stable and it's a fully aromatic compound. So these anilines, depending upon their structure, they may be aromatic or they may be anti-aromatic in nature. So now let's see the other example of a non-benzoid aromatic compound, and that example is of a fused system. Okay, fused, or you can say bicyclic non-benzoid. So this is a bicyclic non-benzoid aromatic compound. Previously we have discussed are the all examples that we have discussed were monocyclic. So this is an example of bicyclic non-benzoid aromatic compound, and that example is of azolene. So what is azolene? So as I told, it's a bicyclic system. So azolene is a 10 pi electron system. So it's an analog to naphthalene. Okay, naphthalene is also a 10 pi electron system. So it's also azolene is also a 10 pi electron system. So it's quite similar as that of naphthalene. So its structure is, so it can be considered as a combination of cycloheptatriene. So this is cycloheptatriene and cyclopentadiene. So one double bond will be over here. Okay. Or so this is not a correct structure because you have two positions over there. So I have to change the positions of these double bonds. So let me change position of these double bond to acquire conjugated type of structure. Yes. So let me so I put double bond over here, then this position is left, double bond over here, then this position is left, then double bond is here, then this is left, double bond is here, then this is left, double bond is here. Now you can see it is a fully conjugated system. All double bonds, they are present over alternating position. So this molecule is a azolene. Now, if we compare this azolene with naphthalene, this azolene molecule is cyclic planar structure with delocalization of these 10 pi electrons, and at the same time it is a polar molecule. Naphthalene is a non-polar molecule. However, this azolene is a polar molecule with dipole moment of around 1.01 dBi. At the same time, the resonance energy of this azolene is 49 kilocalories per mole, whereas for naphthalene it is 79 kilocalories per mole. That means azolene is less stable as compared to naphthalene. So let us see why. This is because of its resonance structure. So naphthalene is a non-polar molecule and its dipole moment is 0. For naphthalene, dipole moment is 0, and azolene is a polar molecule with dipole moment. At the same time, it is less stable as compared to naphthalene. This is because of its resonance structures. Now, if you try to draw its resonance structures, suppose I move this double bond over this position, this double bond over this position, and so I have to move this double bond, okay, over this position. I can't move it over here, okay, because that will lead to two double bonds at the consecutive position. So I have to move negative charge over here, and similarly this double bond remain over its position and positive charge will come over this position. So that will result in a formation of charged structure, charged resonance structure. So there will be negative charge over here because of this double bond, and this double bond remain as such. This double bond will come over here, this has shifted over here, this remains at its original position, and positive charge over here. So you can see over one ring there's a negative charge, on another ring there's a positive charge. Or in resonance hybrid structure, over this ring this positive charge is delocalized, and over this cyclopenta pentadiene ring there's a negative charge is delocalized. So in resonance hybrid structure, over this structure positive charge is there, and over this structure negative charge is there. So you can consider this azolene molecule as a combination of cyclopenta dienyl anion and cycloheptatrienyl cation. So this can be considered as a combination. And since there is a charge separation in its resonance hybrid structure, so that is why it is a polar in nature. At the same time, it is less stable than naphthalene because its resonance structures involve charge separation, while in naphthalene it does not involve its resonance structures does not involve charge separation, and as we know, resonance structures that involves charge separation, they are less stable. So that's why azolene is less stable as compared to naphthalene molecule. So this was aromatic compounds and their examples. More examples you can look from the notes and from book.